Hi everyone, I am Lavanya J from Department of Computer Science and Engineering. Today we'll be diving into Unit 2 of CS22032 Deep Neural Network. Here are the remaining topics under Unit 2: Model Selection, Regularization, Weight Decay and Dropout. So in model selection is the process of choosing the best model architecture or configuration for a given task. It involves comparing different models based on their performance metrics and selecting the one that balances accuracy and complexity. Then next is regularization. So regularization techniques are used to prevent overfitting by adding constraints or penalties to the learning process. So they help the model generalize better to unseen data. Third one is weight decay. Weight decay is a specific form of regularization that penalizes large weights in the network. By shrinking weights during training, it encourages simpler models that are less likely to overfit. And finally, dropout. Dropout is a powerful technique where during training we can randomly deactivate a subset of neurons in the network. So this forces the model to learn redundant representations and improve its robustness. So first we are going to see model selection. So model selection. So it is the most critical step in building effective neural networks. So model selection refers to choosing the optimal neural network architecture and parameters that yield the best performance on a given task. So the goal is to strike the right balance between complexity and generalization. So we avoid both underfitting and overfitting. There are several key components involved in this process. First, architecture design. So this includes um, deciding the number of layers, the number of neurons in each layer, and the types of activation function to use. These choices directly impact the model's capacity to learn and generalize. Second one is neuron selection. So a practical approach here is to start with a small network and gradually add neurons until the performance plateaus. This helps us to identify the optimal complexity. So it is enough to capture patterns in the data but not so much that the model overfits. By carefully tuning these elements, we can build models that are both powerful and efficient. So up next, we will explore the techniques like regularization and dropout that further enhance model performance. So next one is model selection in ANN. So first one is input feature selection. This involves identifying which input variable contribute most to predictive accuracy. By selecting only the most relevant features, we reduce dimensionality, improve model efficiency and often boost performance. Next one is regularization technique. So in regularization technique, these methods help prevent overfitting and improve generalization. So common approaches include L1 and L2 regularization, which add penalties to the loss function based on the magnitude of weights. So dropout which randomly disables neurons during training to encourage redundancy and robustness. And then early stopping. So which early stopping which halts the training when performance on validation data stops improving and preventing overtraining. Finally, hyperparameter tuning. This is the process of finding the best settings for parameters that control the learning process. Key hyperparameters include learning rate, batch size and optimizer type. So learning rate which determines how quickly the model updates weights, and batch size the number of samples processed before updating the model, and the optimizer type such as SGD, ADAM and ORMS prop each with its own strengths. So together these techniques form the backbone of effective deep learning workflows. They help us to build models that are not only accurate but also efficient and resilient. Evaluation strategies. So once we built and trained our neural network, the next crucial step is to evaluate how well it performs. So there are these are the key strategies for a model evaluation. First one is first cross validation. In first class validation, it involves splitting the dataset into training and validation sets multiple times. We train the model on different subsets and validate it on the remaining data. By averaging performance across these folds, we get a reliable estimate of how well the model generalizes to unseen data. Second one is a performance metrics. So the choice of metrics depends on the type of task. For classification problems, we use metrics like accuracy, precision, recall, and the F1 score, each offering a different perspective on prediction quality. For regression tasks, we rely on metrics like mean squared error MSE and the R square score to measure how closely predictions match actual values. Third one is information criteria. To balance model fit and complexity, we use statistical tools like AIC, archaic information criteria, and BIC, Bayesian information criterion. These criterion penalize overly complex models and help us to choose the one that the best explains the data without overfitting. Together, these techniques ensure that our model is not just accurate, it's also robust, efficient, and ready for real world deployment. So this is the basic neural network architecture. At the input layer, we begin with independent variables. So labeled here as 1, x1 and x2. These represents the features or data points we feed into the model. Each input is connected to the hidden layer through a set of weights called gamma weights. These hidden units apply nonlinear transformation to the inputs, allowing the network to capture complex problems in the data. The outputs from the hidden layer are then passed to the final layer, the linear output unit, which through another set of weights known as beta weights. This unit combines the signals and produces a predicated value which corresponds to our dependent variable y. So the network transforms raw input futures through weighted connections and nonlinear processing to generate accurate predictions. This layered structure is what gives neural networks their power and flexibility. So this will explain how the training adjusts these weights to minimize the prediction error and improve the performance. Regularization. So it is a crucial concept in deep learning. So regularization in artificial neural network refers to a set of techniques designed to prevent overfitting. By making slight modifications to the learning algorithm, regularization improves the model's ability to generalize to new unseen data. Some of the most widely used regularization techniques include L1 regularization, L2 regularization, and dropout. So L1 regularization, which encourages sparsity by penalizing the absolute value of weights. L2 regularization, which discourages large weights by penalizing their squared values. Dropout, which randomly disables neurons during training to reduce reliance on specific pathways and promote redundancy. So why redundancy matters? It encourages simpler, more generalizable models. It reduces the risk of memorizing training data. It enhances performance on unseen datasets, and it also makes models more robust, efficient, and better suited for real world applications. How regularization improves generalization in deep neural network. So first, it limits flexibility. So deep learning model are incredibly powerful, but that power comes with a risk. They can easily memorize noise in the training data, leading to overfitting. Regularization introduces constraints on the learning process, which helping the models focus on meaningful patterns rather than memorizing irrelevant details. Second one is it adds a penalty. So regularization techniques often modify the loss function by adding a penalty term. This term discourages overly complex models by penalizing large and unnecessary weights. So the result, a simpler, more generalizable network that's less prone to overfitting. Third, it reduces training accuracy for better generalization. Yes, regularization might slightly lower accuracy on the training data, but that's actually a good sign. The real goal is to improve performance on a new unseen data. By sacrificing a bit of training accuracy, we gain a model that's more robust and reliable in real world scenario. So regularization help us to build models that are not just accurate but also smart, efficient, and ready for deployment. So the most commonly used regularization techniques in artificial neural networks are the tools that help us to prevent overfitting, improve generalization, and build more robust models. Overfitting occurs when a neural network learns not just the underlying patterns in the training data but also the noise. This leads to poor performance on new unseen data. Regularization helps us to avoid this by introducing constraints that guide the learning process. One of the most widely used methods is L1 and L2 regularization, also known as weight decay. These techniques add a penalty term to the loss function based on the size of the weights. The idea is simple, discouraging the model from relying too heavily on any single feature or connection. L1 regularization adds the absolute value of the weights to the loss function. This promotes sparsity, meaning some weights become exactly zero, effectively removing unnecessary connections. The modified loss function looks like this. L equal to L naught plus lambda summation of I equal to 1 to the power of 128 W of I. So here L0 is L0 is the original loss and lambda is the regularization strength and Wi are the individual weights. By applying this penalty, we encourage the network to focus on the most important features, leading to simpler and more generalizable models. L2 regularization in neural network. So it is a widely used technique to prevent overfitting in neural networks. So it works by adding the squared value of the weights to the loss function. So this encourages the model to keep weights small, but unlike L1 regularization, it does not drive them to zero. So the modified loss function looks like L equal to L naught plus lambda summation of Wi the whole square, where L naught here is the original loss and lambda is the regularization strength and Wi are the individual weights. So by penalizing large weights, L2 regularization helps the model to avoid overfitting and improves its ability to generalize to new data. It is especially useful when we want to retain all features but reduce their influence. Dropout. The most effective regularization technique in deep learning is dropout. Dropout works by randomly running off a fraction of neurons in the network during training. In other words, their input is at to 0 for that training step. This prevents neurons from co-adapting too much and encourages redundancy in the network. For example, if we set dropout with a p equal to 0.5, each neuron has a 50% chance of being deactivated during a forward pass. This forces the network to learn multiple independent pathways for prediction, making it more robust. It is important to note that dropout is only applied during the training. When we move to inference or testing, all neurons are active and the outputs are scaled approximately to account for the dropout effect. In short, dropout helps us to build networks that generalize better, resist overfitting, and perform more reliably on unseen data. Here is the simple explanation of the dropout used in neural network to reduce the overfitting. The blue circle represents the input layer, and the orange circle form the first hidden layer, and the green circle represents the second hidden layer, and finally the purple circle are the output layers. So here you will notice that some neurons in the hidden layers are shown as faded or grayed out. So these are the dropped out neurons. During training, dropout randomly turns off a certain percentage of neurons in each forward pass. This prevents the network from relying too heavily on specific neurons and forces it to learn more robust features. As a result, the model generalizes better and avoids overfitting. So, dropout improves the stability and performance of the network by introducing controlled randomness. Working of dropout. So, during training period, the random deactivation with dropout probability p, we randomly select neurons to turn off by setting their activations to 0. Scale surviving activation. To keep the expected activation consistent, we scale the remaining activation by a fraction of 1 to 1 minus p. Mathematical rule. So for an activation of x, the dropout produces this scaling by fraction of 1 and 1 minus p, which ensures the output magnitude remains roughly the same across training steps. During inference, no dropping, that is, all neurons remain active and we use the full network with no dropout applied. Consistent output. So, because we scaled activations during training, we don't need to rescale at interference. Outputs are already calibrated. So, advantages and limitations of a dropout. A widely used regularization techniques in deep learning is a dropout. So, advantages of dropout. First one is reduces overfitting. So, by randomly deactivating neurons during training, the dropout prevents the network from memorizing the training data. Second one is encourages redundancy. So it forces the model to learn multiple pathways for solving a problem, making it more robust. So third one is improve generalization. This model trained with dropout often perform better on unseen data. So fourth one is simple to implement. So most deep learning frameworks support dropout with just a single line of a code. Limitations of dropout. So first one is slower convergence. Because the network is constantly changing during training, it may take longer to converge. Second one is reduced training accuracy. So dropout can slightly lower accuracy on the training set, though it improves performance on test data. Third one is not always effective. So in some architectures like batch normalized networks or very small models, dropout may offer little benefit. It requires careful tuning. So the dropout rate P must be chosen carefully. Too high and the model may struggle to learn. Too, if it is too low, and it may not prevent overfitting. So dropout is a powerful tool for building generalizable and resilient models, but like any technique, it must be used thoughtfully. Early stopping. It is also another regularization method. With early stopping, we monitor the validation loss throughout the training. As long as the validation loss keeps improving, the model continues to train. But the moment of validation loss stops improving or starts to worsen, we stop the training process. This prevents the model from overfitting because it stops learning patterns that only exist in the training data. Early stopping requires a separate validation state, and it's commonly used along with another regularization techniques like dropout or weight decay. It is an effective, low cost way to ensure the model generalizes well. Here we can see how early stopping works by looking at the behavior of the training and validation error over time. On the horizontal axis, we have the number of iterations, and on the vertical axis, we have the error. So notice the two curves. The training error keeps decreasing steadily as the model continues to learn. But the validation error behaves differently. It declares at first, reaches a minimum point, and then begins to rise again. That raising validation error is a clear sign that the model has started to overfit. It's memorizing the training data rather than learning general patterns. The dashed vertical line marks the early stopping point. This is the moment where the validation error is at its lowest. Training is stopped right here before the model begins to overfit. So early stopping help us to capture the model at its best generalization performance. So not too early and not too late, but exactly when validation error is minimized. Regularization techniques. Advanced regularization and optimization techniques beyond L1, L2 and dropout. There are several other powerful techniques that help neural networks generalize better and perform more reliably. First one is data augmentation. These are also comes under regularization techniques. So fourth one is data augmentation. So in this technique, it increases the size and diversity of the training dataset by applying transformations to the inputs. For example, rotating, flipping or cropping images. By training on slightly different versions on the same data, the model learns to generalize better. So data augmentation is especially common in computer vision tasks, whether it dramatically improves the robustness. Then next one is a batch normalization. So batch normalization normalizes the input to each layer, ensuring they have consistent distribution. This leads to faster convergence during training and also acts as a form of regularization. In fact, in some architectures, batch normalization reduces the need for a dropout altogether. Third one is a label smoothing. So in label smoothing, instead of using a hard labels like a 001, we use soft labels such as 0.1, 0.1, 0.8. This reduces the model's confidence in its predictions, discourages overfitting, and improves generalization. So label smoothing is particularly useful in classification tasks where models tend to become overly confident. Together, these techniques, data augmentation, batch normalization, and labs label smoothing, which makes our models more robust, efficient, and better suited for real-world applications. So next one is batch normalization. So also called it's often called as a BN, which works by normalizing the inputs of each layer so that they have zero mean and unit variance. In simple terms, it ensures that the data flowing into each layer is well behaved and consistent. So why does this matter? Because it stabilizes the training process and allows networks to converge much faster. Without batch normalization, training deep neural networks can be slow and unstable. As the distribution of the inputs keeps shifting during learning, a problem known as internal covariance shift. By applying batch normalization, we reduce this shift, making optimization easier and more reliable. In practice, batch normalization often acts as a regularizer too, reducing the need for a technique like dropout in certain architectures. So, batch normalization not only speeds up training but also improves generalization, making it a cornerstone of modern deep neural networks. Batch normalization is applied between layers to normalize their outputs. So it ensures that each layer receives inputs with stable mean and variance, which keeps the network stable during training, allows faster convergence, reduces sensitivity to weight initialization. So in this diagram, each hidden layer's outputs are normalized before being passed to the next layer. This helps the network learn more smoothly and consistently. Goals of batch normalization. Now we understand that batch normalization is the key goal and why it is so widely used in deep learning. First, faster training. So by stabilizing the inputs to each layer, batch normalization allows us to use higher learning rates. This speeds up convergence and makes training deep networks much more efficient. Second one is reduced internal covariance shift. During training, the distribution of inputs to each layer can change as weight or updated. This shifting distribution known as internal covariance shift, which slows down learning. Batch normalization, which reduces the effect, keeping inputs consistent and easier to optimize. Third one is act as a regularizer. Batch normalization introduces a slight noise due to mini-batch statistics, which acts like a regularizer. In many architecture, this reduces or even eliminates the need for dropout. Fourth one is improved generalization. By stabilizing, training and reducing overfitting, batch normalization helps models generalize better to unseen data, making them more robust in real-world application. In short, batch normalization accelerates training, stabilizes learning, and improves both efficiency and generalization, which is why it has become a standard component in modern deep neural networks. Working of batch normalization. So how batch normalization works? So first step 1, receiving a mini batch of inputs. Suppose a layer receives a mini batch of inputs denoted as x equal to x1, x2 up to xn. Compute this mini batch with mean and variance. So second step is computing the mini batch mean and variance. We calculate the mean of the batch as mu b equal to fraction of 1 by n to the sum of I equal to 1 to the power of m of xi. This represents the average input value for the batch. Next, we compute the variance to measure how spread out the inputs are. So, third step is normalizing the input. Each input is standardized using the formula xi hat equal to fraction of xi minus mu b divided by square root of sigma b square plus epsilon. So it is the standardization. So here sigma b square is the batch variance and epsilon is a small constant added for numerical stability. This ensures the inputs have zero mean and unit variance. So next step is scale and shift with learnable parameters. So finally, we apply a scaling and shifting transformation using two learnable parameters, gamma and beta. So yi equal to gamma xi gamma hat xi plus beta. During training, the network learns the best values of gamma scale and beta, allowing it to restore flexibility while keeping the benefits of normalization. So, batch normalization standardizes inputs, stabilizes training, and then reintroduces flexibility through learnable parameters. This combination makes deep networks train faster, more stable, and better at generalizing. So next another regularization technique here is the weight decay. So weight decay works by penalizing large weights in a neural network. If the weights become too large, the model risks memorizing the training data instead of learning general patterns, which leads to overfitting. So to prevent this, we add an extra term to the loss function that discourages the model from assigning large values to the weights. This penalty keeps the weights small and controlled, encouraging the network to learn simpler, more generalizable representation. So white decay is um, closely related to L2 regularization, where the squared value of the weights are added to the loss function. By shrinking weights during training, the model becomes more robust, efficient, and better suited for unseen data. So weight decay helps us strike the right balance, powerful enough to capture patterns but restrained enough to avoid overfitting. White decay operates inside the neural network. So first step is start with the original loss function. Normally the loss function measures the difference between the predicted output and actual target. We will call this as L naught equal to mathematical m of loss predicted or actual. So second step is adding a penalty term with white decay. We modify the loss function by adding a penalty on the size of the weights. This penalty discourages the network from assigning very large values to its weights. So L equal to L naught plus lambda summation of wi the whole square. Here lambda is the weight decay coefficient, also known as the regularization strength, and Wi are the model's weights. So third one is the optimizer role. So the optimizer does not just try to minimize prediction error, it also works to keep the weights small. This balance helps the model avoid overfitting and improves its ability to generalize the unseen data. So in short, weight decay ensures that our neural network learns patterns without memorizing noise, resulting in simpler, more robust models. Weight decay versus L2 regularization. So in this two techniques are often considered equivalent but implemented slightly differently. So first L2 regularization. In L2 regularization, we add a penalty term directly to the loss function. This penalty is proportional to the squared value of the weights. The optimizer then minimizes both the prediction error and the penalty, keeping weights small. Second is weight decay. So weight decay achieves the same effect, but instead of modifying the loss function, it modifies the weight update rule in the optimizer itself. So the update rule looks like this. Here W beta is the learning rate, and n lambda L is the gradient of the loss, and lambda is the weight decay factor. This formulation directly shrinks the weights during each update step. So weight decay in neural network, how to choose the right value for weight decay. So the typical value of weight decay is weight decay coefficient lambda, range from 10 to the power of minus 5 to 10 to the power of minus 3. These values are small enough to avoid underfitting but strong enough to keep weights under control. However, there is no one size fit to all answer. So the optimal value depends on the data set, the model architecture, and the task at hand. That's why we rely on ruling methods such as cross validation or grid search. These techniques allow us to systematically test different values of lambda and identify the one that yields the best generalization performance. So when to use a weight decay? Now we understand how weight decay works. So using weight decay, when we use the weight decay. So your model is overfitting, meaning it achieves very high accuracy on the training set but performs poorly on the test set. So you are working with complex models such as deep neural networks with many parameters where the risk of memorizing noise is high. So when to avoid or reduce the weight decay. So your model is underfitting. In other words, it's too simple and already struggles to capture the patterns in the data. Then we will avoid the weight decay. Then if you are using architectures that already include strong regularization techniques such as batch normalization or a dropout. In these cases, adding too much weight decay can unnecessarily restrict the model's learning capacity. So the key takeaway is here is the weight decay is powerful tool against overfitting, but it should not be applied carefully. Using it to take overly complex models but ease off when your model is already struggling or when other regularizers are in play.